If you sat down and tried to implement Prim's algorithm as we described before, you could do it, but what you'd end up with is something that's a little inefficient. So for example, when we got to this phase in the algorithm, we have all of these purple edges to consider. So we'd have to first find all of the purple edges that are coming out of all of the vertices that are along our minimum spanning tree, and then we need to iterate over them and find the maximum. Now there's a better approach, which I'm about to describe, which uses some cleverness and some data structures to make Prim's algorithm faster. We're not even going to talk about the runtime of the conceptual version because we didn't present it as a full algorithm. But suffice it to say, you could see that looking at a bunch of purple edges isn't going to be a great strategy because we're looking at them over and over again. And so this approach for Prims is going to be a little confusing at first. Let me just make that clear. And I think you'll need to sit down with this demo and step through it and see what's going on. But it turns out that what we're about to describe is exactly the same as the conceptual version of Prim's algorithm. It's just things are done in a slightly different order and it feels a little different. Okay? I think it's really cool and clever, but just be warned, it'll seem strange at first. So how this version of Prim's algorithm works, it's the exact same algorithm, just kind of written out a little differently, is we're going to start by inserting all of our vertices into the fringe priority queue that we set up. And in this case, we're going to store all the vertices in the order of the distance from the tree. So it's kind of like Dijkstra's, just I have the word tree here instead of source. And then what we're going to do is repeatedly remove the closest vertex from the priority queue and relax all of the edges. And that actually, as it happens, will turn out to be the same as the conceptual picture. So let's see how. So we start with vertex 0 on the fringe. Let's get rid of this thing. All right, I learned a new trick. Let's inspect. Let's find the stupid box that pops up. Where are you? Where are you, box? There we go. Okay. You're out of here. Okay, anyway, it's gone. So what we've got here now, we have vertex 0 on the fringe. I click, and at this point now, this vertex is removed, and we consider all of its outgoing edges, and we relax them. Now in this case, what that means is these distances are going to get set to 1 and 2, respectively. So we update their values on the fringe, and we set a distance to and an edge to value. Now, this might seem a little peculiar because it seems like Prim's algorithm is supposed to only add one edge at a time, but it seems like we've added 2 because I set 2 edge 2 values. Well, don't worry. What I've got here is dotted lines indicating that this is just the best known edge. We haven't actually committed to including them in the minimum spanning tree yet. Now, where the commitment happens is actually when I remove this next vertex. So when I remove vertex 2, this edge, I'm going to mark it as solid. Now, that doesn't change anything in terms of the Java data structures other than the removal from the fringe. The distance to and edge to arrays are not changed, but I'm going to bold it here to remind you and I that this is an edge that the algorithm has now committed to. This will never change again. Okay? So in other words, in this version of Prims, where we're using these data structures like a fringe and this distance to an edge to array, whenever we remove a vertex from the fringe, that's the point where we're committing an edge to be part of the minimum spanning tree. It's the equivalent of adding an edge in the conceptual version. So that might seem a little mind-bending, that somehow removing a vertex is equivalent to adding an edge, and yet nonetheless it is true. So let's keep going, and hopefully it'll make sense. And what you can do is compare what we're doing in this demo with what we did in the previous one, and you could see, hopefully, the correspondence between the two. Okay, so the next thing that would happen, now that we've removed vertex 2, is we'll consider all of the outgoing edges. Now, you and I know that the conceptual version of Prim's algorithm is going to ultimately pick this edge and add it to the minimum spanning tree. But this version of Prim's, it's a little more clever. It's going to avoid looking at this edge again because we already did that, right? We already considered that when 0 was the active vertex. So we're only going to look at these 3 edges, which saves us a little time. And we're actually going to do something a little funny, which is instead of just adding 1, the edge of weight 1 to the spanning tree, we're also going to tentatively add the edge of weight 15 because these 2 edges are better than the old best distance to the tree. Now, one difference between Dijkstra's and Prim's is, of course, we're measuring the distance from the tree, not the distance of the source. So this number is 15, not 16. Okay. So at this point, these two vertex distances get updated. This one does not. And the reason it does not is because we already have a better way to get to vertex 1. So we'll update the fringe, we'll update the edge 2 and distance 2. And at this point, we basically have 2 provisional edges that we've just added to the minimum spanning tree. We have 1 leftover provisional edge, and then we have one edge that is never going to be part of the spanning tree, no matter what. Okay? So now I have a challenge for you. Try and figure out what happens next. The first thing you need to do is figure out which vertex gets removed next, and then which distance to and edge to values get changed as a result. So pause the video, really do it, and see what you come up with. All right, so the next vertex to get removed will be vertex 4. So here are the outgoing purple edges that it needs to consider. It does not need to consider this edge again. I've bolded it. And what I'm noting there is, I mentioned before that when we remove a vertex from the fringe, that's the equivalent of adding an edge in the conceptual picture. So I'm just making that clear here by bolding it. I've also bolded it on the other side here. And now we have these 4 edges to consider. So is 3 an improvement over 2? No. Is 2 an improvement over infinity? Yes. Is 3 an improvement over infinity? Yes. Is 4 an improvement over 15? Yes. So I'll update these 3 values to be 2, 3, and 4 respectively. I update their values in the fringe. I update their edge to and distance to values. And in this case, what we end up with is, again, 3 provisional edges. Okay. Now we'll notice that I've changed 15's marking to no longer be a dotted line, and that reflects the fact that when we look at the Java data structure, this row 5, its edge to is now 4 instead of 2. So it's no longer dotted. Now you'll recall that in the conceptual version of prims, we had a tie, and here we have a tie again. We could either commit to this edge, or we could commit to this edge. Both are valid choices. Both are at the top of the fringe, so to speak. And in this example, I'm going to tie break the other way, just for being different. So this time, I'm going to make this edge solid, and we'll consider 1's outgoing edges. Okay. So now we have this edge that's of weight 11. 11 is worse than 2, so we don't use it. And I'll quickly note that there's no need to consider the weights of these 2 edges that have weights 5 and 3, because those are connecting 2 vertices that are already marked. And I am not showing a separate marked array, but it's trivial to imagine that each of these vertices has a true value that says these are marked. So since these are already marked, then we don't need to consider these edges again. So we're saving some time again. Because remember, again, the whole goal of this stranger version of prims is we're trying to avoid looking at tons of purple edges. So try and imagine, right here, if we were looking at all of the outgoing edges from every white vertex to every green vertex, there would be many more that we're considering. But because we've done this clever stuff where we're keeping around old work, for example, that 4 and 6 have a best known connection of 3, we don't need to think about these edges anymore. We don't need to think about these edges, or we never should have been thinking about those, and so we saved ourselves some time. So 11 is not better than 2, so we don't do anything with that. So next up, our priority queue has 3 on top, so that's our next vertex. And again, in the conceptual picture, which is what this whole algorithm is supposed to copy, that means we're going to commit to this edge, basically. Okay, is 1 better than 3? Yes. So we'll update that vertex, its priority, to be 1, and we will update its distance to an edge to. So now 6 is the top item, and so we've removed that, and so this is bold now. Oops, I bolded 1 step early, so okay, hopefully that wasn't confusing. And then finally, we end up updating the distance to 5 so that it is now 1. And so now, because we are done, I've already pre-bolded that edge, and voila. So that's a different way of implementing prim's algorithm that turns out to be exactly the same ultimately as the conceptual version, but it has a better runtime, as we'll discuss in a moment.